Welcome everyone to Jam Academy. Now so far we have been dealing with cases in which the force is constant. So I have shown you how to calculate the work done by a constant force acting on a given system. But the truth is, it is not in all instances in which the force acting on a given system is constant. As a matter of fact, the force can vary with position as well as it can vary with time. So how do we calculate the work done for a variable force? Now, in this particular section, I will concentrate on position-dependent forces. Forces that depends only on the position of its point of application. Take, for example, the force of an extended or compressed spring. It depends on the amount of stretching or compression of the spring. If I shoot maybe using a slingshot and I shoot a stone upwards or throw something upwards, as the object goes up, the gravitational pull of the earth on the object changes with position. This is a good example of a position-dependent force. So the question is, how do we calculate the work done by this force? The trick is simple. By the way, as a reminder, the work done by a constant force, is equal to that force multiplied by dot dr. This is what we have been using so far. In other words, W is equal to F delta R, the cosine of theta. This is the formula we use when the force is constant. But what if the force is not constant? What do? If you look at this graph, this is the graph of a force whose value changes with position x. Now, in order for us to calculate the work done by this force, what we will do is we will break down the displacement vector into very small increments. The increment is so small such that the applied force within that increment is presumably constant. So if you look at one of the increments, I'm going to call this delta x, you will recognize that the force within this increment is approximately constant. So we can calculate the work done by this small force within this small increment. And so we are going to use here delta W because it is the work done over that very small increment. So this is going to be equal to F xi multiplied by delta xi cosine of theta. Remember that delta xi is so small such that the force within that increment is presumably constant. So the total work done will just be equal to the sum. We are summing all the work done for all the increments that span from xi to x final. That means that this is going to be equal to delta Wi, which implies that the total work done will be equal to the sum from I up to n. Remember, there are n of these increments. So the total work done will be the limit as delta xi turns to 0 of the sum from I to n. Remember, delta wi is just gonna be f xi delta xi, the cosine of theta. The cosine of theta. We can further expand this to be equal to, this would mean that the total work done will be equal to, remember that this is just the definition of the integral from xi to xf. So we can clearly say that this will be equal to the integral from xi to xf of f of x dx cosine theta. In other words, the total work done, W, is equal to the integral from xi to xf f x cosine theta dx. This is the work done by a variable force. This is the formula to calculate the work done by a variable force. Another way that we can represent this is just the fact that the work done, W total, will be equal to the integral from xi to xf fx dot dx fx dot dx. And you can clearly understand that because f dot dx is just equal to that quantity. Now, when you look at this carefully, this is actually equal to the area bounded by the graph. This is equal to the area bounded by the f x versus x graph. So the total work done by the object is simply equal to the area under the force versus x curve. Keep that in mind. This is really beautiful, and if you have any questions, please do not hesitate to ask in the discussion forum below. Thank you so much and remain blessed.